Okay, so good afternoon again. Welcome to APNIC eLearning web class. This is IPv6 Overview. This is the third session that we are doing for this day. We usually do IPv6 related topics on the first Wednesday of every month. So this is our IPv6 eLearning Wednesday. Today is the 5th of March in 2014. It's 2:30 in the afternoon from where I'm broadcasting, which is in Brisbane, Australia. This class will run for 1 hour. At the end of the session, I will ask you to fill in a survey just to get some feedback about the quality of this class. Now, before I move on, I'd like to also introduce myself. My name is Cheryl Hermoso. I work as a training officer for APNIC. APNIC, as you know, is the Asia Pacific Network Information Center, and it's the internet registry for our region. Now, as a training officer, I conduct these topics: DNS, DNSSEC, network security, IPv6, Internet Resource Management. We also do some routing and advanced routing, BGP topics as part of our curriculum. Again, as a reminder, I would be writing down the link to the survey later on, so if you can, please try to fill that in. All right, so with that, I guess we can continue and try to have an understanding, a better and broader understanding of IPv6. IPv6, you've probably heard of it being talked about in the internet community a lot over the past, probably even more, 5 years or so. So what exactly is IPv6? We will try and cover that, and to be able to understand what it is and what its function would really be, let's have a look at the features and some functional improvements of IPv6 as compared with IPv4. Let's look at the different addressing models. Now, there are different IPv6 addresses. Our concern here is just to look at the model, not the different classifications of IPv6 addresses, because we probably don't have enough time to cover all of that. Now, we will also look at the differences between the headers of both IPv4 and IPv6 to be able to understand the changes, the functional improvements as well. Because when you look at the headers, you will understand the different functions by looking at the different header fields. We'll look at interface ID, which is something new perhaps with IPv6, and also the different types of prefixes that are available on the global IPv6 internet. All right, so that's what we're planning to cover. Hopefully that is enough content for us to cover within the 1 hour session that we have. All right, so let's start off with IPv6. And before we jump straight ahead into that, I'd like to just have a review of a protocol, just leading to the answer of this question. So what is a protocol? As you know, protocol is probably something that is inherent in internet communications. So protocol is a means to define the rules for data communication. It's like it's establishing a common language that can be used by different devices that are connected to the internet, so that they will have meaningful communication, so that it will be possible for them to understand when they are sending bits and pieces, digits, zeros and ones all throughout the line. So protocols achieve this by coming up with a definition of the information that is required for this type of communication. So we have TCP/IP, which is the protocol stack, okay, which are basically groups of these different protocols, actions that are making up the entire data communications process into different layers. So that is a protocol essentially. You have a way, a rule that is followed by the different devices that communicates via the data lines. An internet protocol is essentially a protocol that is for IP, for the internet. In our days, we use the TCP protocol stack, okay, as the main language used on the internet, okay. It is responsible for the proper delivery of data to a target destination. Okay, and that's internet protocol. So when you talk about IPv4, IPv6, it is an internet protocol, right? So IPv6, you can say, is a version of the internet layer protocol in the TCP/IP suite of protocols. The goal essentially is the same as IPv4. The goal is, okay, to deliver data, to deliver packets from one node to another node, to have meaningful conversation between these different nodes. IPv6 is meant to replace, or possibly if you look at it from our standpoint nowadays, it's meant to complement the currently existing IPv4. Okay, so IPv6 is a new protocol, but the word new here in this case is being used very loosely because technically it is not a very new protocol anymore. It has been around since the late 1990s. The protocol itself was standardized in 1998. So although most of us at this point, it is 2014 now, most of us are still new with IPv6, are still trying to get to know what it is, or what it is for, and how we are going to use it and implement it. Okay, the original specifications of IPv6 was made available since the 1990s. Okay, it was meant to replace the current protocol we are using today, which is IP version 4. Okay, we have another person in the class, Arpan from Nepal. Would you be able to let us know if you can hear us properly or not? So we're not sure about the audio. Let me just ask. So let's just pause for a minute and then ask Arpan if he can hear us properly. Alright, good. Thank you very much for that response, Arpan. Hopefully the quality of the audio is good from your end. And Noel, please check on your end as well whether the quality has improved or not. Okay, so I guess we can continue. Arpan, we were just starting. We were just describing what IPv6 is as a sort of introduction to the entire session. So as I was saying, IPv6 is an internet protocol, and you can say that it is a version of the internet protocol. So it's version 6 as compared to version 4 of IPv4. IPv4, as you know, is the most common one that we are using nowadays. It's the current protocol that we're using for interconnecting networks and host devices. So if you are interested, the standard specification for IPv6 is an RFC 2460. Okay, it contains the standard specifications of IPv6. Now, RFC, as you know, it's a standard document by IETF. It contains all the specifications, standards, behaviors, protocols that are related to the internet, and it is published by engineers, computer professionals. Some of these RFCs are standards, which means that manufacturers should adhere to these standards, and they are adapted and published by a body called IETF, or the Internet Engineering Task Force. Now, a lot of people have been asking me, I don't know if it's out of curiosity or just trying to make sense why we jump from IPv4 all the way to IPv6. There is, in fact, an IP version 5. IPv5, although it is not a standard. IPv5 is for Internet Stream Protocols, the ones that we're going to use for streaming or web contents. But again, it's an experimental protocol. It was never standardized. If you are interested, that's RFC 1190, but again, that's not a proper standard, therefore it's not necessarily implemented on all your manufactured devices. Now, if you read through documents in the early days, IPv6 was also called IPNG, or the IP Next Generation. So starting from the time that they formed a group that will look after the many proposals that are being sent through up to the time that they decided which specifications would come into the proper standard, or the right standards for IPv6, they used to call it as IPNG. There was even an IPNG working group that looks after these things. All right. So when we talk about changes in IPv4 and IPv6, we are most concerned in this layer. Okay, so this is just to show you, this is a diagram that shows you the TCP/IP protocol suite. But although there would be minor effects when it comes to the application layer, or probably even the transport layer, most of the changes that will happen, okay, protocol-wise, is limited only to this area. Okay, we're only talking about IP here. Alright, so I'll give you a bit of background about IPv6 and how it started. Now, if you are aware of the early days of you, if you've been in the internet industry for a while, you would know that the way that we distribute addresses in the early days was classful. So probably if you read through some network-related books and different lectures, you would know about Class A, Class B, and Class C. So that is how we distribute IP addresses. So that's not actually that's not very mindful of the future. Well, they never thought that the internet would grow. As you know, the internet is an experiment that has gone out of the lab. So in the early days in 1990, so internet started in the 1970s, it started growing in around the late 1980s. It has started getting say some people have become interested, some organizations have become interested, and they started connecting to ARPANET in the late 1980s. So as early as 1990, there was a first wake-up call by a guy named Solensky in IETF that mentions about IPv4 address exhaustion. What is address exhaustion? Well, IP version 4 has a pool of addresses, okay, a pool of addressable devices can be addressed using that basically that IPv4 pool. So as early as 1990, they saw that if they are going to keep on spreading or distributing addresses the way that they do right now, which is classful addressing, then at some point in time, okay, this pool will be exhausted. Obviously, because well, it is a limited pool. It's not an infinite pool. All right. So at some point we will have run out of these IP addresses. And from their calculations, since they were giving a lot of Class A's and Class B's at the early stages, they saw that maybe if we continue giving Class C's at this point, which is around 1996 to 1998, we would have run out of IPv4 addresses. Alright, so that is as early as 1990. What year are we in now? It's 2014. So in 1994, around December, they formed a group, they call it the IPNG Working Group, that would look after the management or look after some ways in which we can address this possible issue. So some of the ways that they come up with are either long-term or short-term. The short-term solution was first to use VLSM, variable length subnet masking, or more typically you would have heard it as classless addressing. So we're not using classful addressing anymore, so we're not using as much or wasting as much space because we will only distribute if they need a certain amount of space and they're not tied up with only these different classes. Another way is to come up with or to form the regional internet registries or RIRs. So IPNIC is one of those RIRs that are charged with properly distributing addresses to people, to organizations that actually need those addresses. So right now, if you read through the policies, you would see that there is a phrase there, demonstrated need. You should be able to demonstrate or show or justify that you actually need an IP address space before it will be provided to you. And even with that, IP addresses are on a lease basis, meaning you have to renew it on a yearly basis, okay, so as to show that you still need to use those IP addresses. So that's how it is. Those are short-term solutions. Now, the long-term solution is to come up with a new protocol. That's why they have IPNG. The reason is to find, okay, proposal or to seek proposals from the community, okay, that will be used to come up with a new protocol. So they saw a lot of proposals being sent in, okay, in the IPNG networking working group. Some of them said that let's use a fixed size IP address, maybe from 32 bits, which is what we're using in IPv4. Why not make it twice as large or maybe 4 times as large? So that was when the proposal to use 64 bits and 128 bits came out. There were also proposals to use flexible, okay, address ranges, meaning let's start off with 64 and make it so that we can easily extend that to maybe 128 or maybe even more as we see fit in the future. There were proposals about changing the way the addressing would work. There were proposals to add different features to the new IP version, right? So you will see about those changes in a later slide. So in around 1995, one of the recommendations, one of the proposals, as I've said, is to use 128 bits, and they stuck with using 128 bits. The first version of the IPv6 address specification came out as RFC 1883 in 1995, and the first standard version, which is RFC 2460, was made available, was published in 1998. Now, there have been few things added over the past years to this RFC, so you can see updates added onto the RFC if you look at it, if you search it online in the IETF website. So why do we need IPv6? So I gave you a brief background, I gave you the reason behind it. That's because of IPv4 address exhaustion. Again, as early as 1990s, they saw a need to increase the number of the IPv4 address space. And if we continue to deliver or to delegate IP addresses the way they did in the early days, then they would run out of space. And what is the implication of running out of space? The internet, as you know, is growing. It keeps on growing, and the pace that it grows is very rapid. Okay, so you need a way to address that issue. If at some point we don't have address space, well, the internet will still remain. The internet will still work as it is today. But the problem there is, do we have enough? Okay, for those that wanted to still connect, to still join the network. And with the currently we have like Internet of Things, we have mobile devices, even equipments at home, even our home appliances, our car, everything can now have that small chip that contains the networking functionality. So we need to be able to address the growing number of devices that would need to connect to the internet. And IPv6 is the answer to that. IPv6, of all the extra features, the most important one is that IPv6 provides us with a much larger IP address space than compared to IP version 4. Now, IPv4, as you know, is 32 bits, so that is equivalent to about 4.3 billion addressable devices. So IPv6 has 128 bits. Address-wise, that's 4 times as large as IPv4. However, when you look at the entire pool, that's not just 4 times larger, that is heaps larger. Because this is exponential, that's 2 raised to 128, which is roughly around 3.4 times 10 to the 38 possible addressable devices. So that's quite a lot, right? So you need to be able to address the issue. That's why we have IPv6. I'm not saying here that right now we don't have any more IPv4 addresses. We do, but we are on a limited supply. If you look at the different RARs, so the way that you distribute IP address is coming from IANA. IANA is an implementing arm of ICANN. So IANA, or the Internet Assigned Numbers Authority, they are the ones who distribute them to the 5 regional internet registries around the world. APNIC is the one for our region. All right. So in 2011, IANA has distributed the final 5/8 blocks to the 5 RARs, and that was around February, and around April of that same year, APNIC has started distributing from that final /8. So right now, I think we have about 0.85, or 85% of that entire /8 block. So if we have distributed all of them, we won't have anything else to give. Okay, RIPE NCC, which is the RAR for Europe and Middle East, they have also started distributing from the final /8. And it is expected that soon enough, maybe later this year or early next year, AREN, which is the one for the American region, and also LATNIC from Latin America, would probably also follow and start distributing from their final /8s. So again, what I'm saying here is we have a very limited amount of IPv4 addresses, and considering that the growing need for that is like exponential, then we need to be able to cater for that need. Now, aside from that functionality, that bigger address space, IPv6 also presents or has introduced some new functionalities and some new ways and improvements as compared to IPv4. Because why not? We are coming up with a new protocol. When we came up with the IPv4 or the TCP/IP protocol suite, we don't have as much experience. Now, after a few years, maybe about 10 years that we have been using IPv4, we've learned some things from it. Maybe there are features there that we don't exactly need, or maybe we can just add it as an optional function. Okay, if needed, then we'll add it. So in IPv6, they have addressed some of those issues. So these are the new functionalities or new things that have improved in IPv6. So first is an increase in address space. So increase in address space, this one is something that you should all be familiar by now. Increase from 32 bits to 128 bits. Now, not all IPv4 addresses that we have are usable. Okay, so out of that 256 /12s, okay, only 75% of all that, okay, is basically part of what we call as the public addresses, okay, the reachable addresses in the global IPv4 internet. Those are the ones that are distributed by the regional internet registries. If you have a public IP address, your host, your machine will be reachable from anywhere on the internet. You have an identity, you have a presence on the internet. So again, only 75% out of the 4 billion addresses are actually the ones that we're using. How about the others? Either they have been delegated early on, which is what we call as historical addresses, or they are used for other purposes, maybe for experimental purposes, maybe for private addresses, for multicasting and all of that. Okay, so the global pool has been officially exhausted this in 2011. Again, in IANA has already given out that final /8 to all the 5 RIRs. That was in February, and from at this point, if you look at the NRO report, NRO is a number resource organization. If you look at their website, they they publish a report, I think on a quarterly basis, that gives you a rough number of the current state of the IPv4 address pool. So if you look at that, you'll see that for IPNIC, it is about 0.8 or 0.82% of the entire /8 block. Right, so that is one thing with IPv6. Also, IPv6 provides what we call as stateless auto-address configuration, or roughly it is also called a SLAC, or more simply, you just call it an autoconf or auto-configuration. What is auto-configuration? This is something new with IPv6. Now, we will have some slides later on that will possibly illustrate this better, but essentially, with stateless auto-configuration, it makes it possible for your machines to connect to the IPv6 network, okay, without having to do anything. Now, you don't need an external DHCP server to provide an IP address. You don't need an administrator to manually configure your network, your devices to have an IPv6 address. It will automatically have an IPv6 address, and that means that it can communicate locally. Within the local link, it will be able to send and receive packets from all the other devices. That is stateless auto-address configuration. You have to remember that when they were coming up with the specifications for IPv6, which is around 1990s, that was also around the same time that DHCP is being developed. All right. Next is fixed header size of 40 bytes and 64-bit header alignment. Now this would mean a better router and switch performance. With IPv4, now we will look at this in the next slide from here. Basically, what you see there is you will see a difference when IPv6 and IPv4 headers. Now IPv4 itself has 20 bytes, but this is not fixed size, meaning it can change. You can increase depending on the options that are added. But IPv6 is fixed size, meaning that your router does not have to do some extra things, okay, do some extra calculations just to find out the size of your headers. Therefore, somehow it adds to the to better performance of your routers. And it's also 64-bit aligned. Nowadays, most of the routers, most of the equipment are all using 64 bits. But early in the days, we have 32 bits and 64 bits, and 64 bits are more preferred because of its alignment with all the other, like the memory, the caching, and everything. Next, it has no hop-by-hop segmentation. Now this one is what we call as path MTU discovery. MTU is the maximum transmission unit, right? MTU. Now for each link, there is an MTU size, okay? So usually it's at 1500. Now with IPv6, there is what we call as no hop-by-hop segmentation. Now if you're sending, say, a packet, a message, from router A to router D, and it has to pass through two other routers, maybe router B and router C. Now each of those links will have an MTU, right? Maybe it's 1500, it can be more, it can be less. Think of it as bandwidth, the size of the packet that is allowed to go through that link. Now, because it changes, let me just add this, sorry, there's so many things going on the background. People logging in, more hosts coming in, which I don't quite understand. But, well, anyway, let's get back to this. I was talking about no hop-by-hop segmentation. So essentially, if a packet has to go through from router A to router D, and it has to pass through router C and router B and router C. If at some point in one of those links, it is set to a lower MTU size, what happens is router A will still send that message, it reaches router B, it reaches router C, but then since the link does not allow bigger MTU size, it will be dropped. So it goes back to router. Router A notices that it wasn't sent through, it will now resend the packet. With IPv6, that's not necessary. It has a knowledge of the MTU size, of the biggest size of the packet before it formulates and sends that packet out. Okay, so that when it sends out, it is the right size, the right amount to pass through all the links possible. But this is an optional basis, all right? Meaning it can try and find out the MTU size of the links, but the routers in between has the option to just ignore it. It has built-in features for multicast and anycast, and this is also very much related to this last one, which is no broadcast. IPv6 does not support broadcast. And in order to achieve some of the things that you do with broadcast, we use multicast and anycast. We'll see more on that later on. It eliminates triangular routing and simplifies deployment of mobile IP-based systems. So basically for this one, this is an ongoing I think an ongoing feature. There have been changes every now and then about it, but basically in mobile devices you have what you call as triangular routing. So if you are roaming, if you need to send a packet to your destination, basically it has to go through, or it has to pass through your home network before it is sent through your to your destination. So it's using 3 nodes. So with IPv6, it tries to make the communication faster so as to eliminate the part where you have to get through or you have to do binding updates with the home network. It has built-in support for IPsec, VPN, and QoS tagging. So I think this is why some people would say that IPv6 is more secure than IPv4. IPv6 has built-in support for IPsec, and IPsec is a type of VPN. So essentially, we want here secure communications that is end-to-end, not just network to network. So each device, if you have an IPv6 device, you have IPsec enabled there, you communicate with another device with IPv6, then the communication between those two machines are secure. And of course, we've talked about not having broadcast. So you might ask, if there is no more broadcast, how do we find out the machines in a particular network? Now we will look at that later on. I have, I think, 1 or 2 slides that illustrate how we would go about discovery. So that's how you discover the different machines on a particular link, and we will not be using broadcast there, we will be using multicast. Any questions so far? If there is any question, just please let me know, write them down on the chat so I can have a look at it. Otherwise, I'll just continue with the session. Okay, next one is about IPv6 addressing models. Now, this is in RFC 4291, so that discusses essentially the different IPv6 addressing models. So when you go and when you see an actual IPv6 address, you would understand whether it belongs to any of these different addressing models or addressing types. So we also have this in IPv4. So notice we have 3. We have unicast, anycast, and multicast. We don't have broadcast here. But the functions are the same, right? With unicast, this is a one-to-one relationship. So you have a packet, it is being sent through from one interface, and it is received in another interface, only a single interface, 1:1. So the packet contains a single, the source address pertains to a single machine, the destination address also pertains to a single machine. Okay, that's unicast. That is what most of us are familiar with. Now the other two are anycast and multicast. Multicast, it's easier to describe multicast first before anycast, so I'll go and describe what multicast is. So multicast basically is one to many. So a packet is sent from a single source address to a multiple destinations or multiple interfaces. So if I can make an analogy here, we can think of an email that is sent to a group. So if you're part of a group, you receive the email as the rest of the people who are members of the group, right? So, but the person who created the email, okay, when he wrote down the email, essentially he had to just make one, and it is, when he sends it out, it is sent to everybody. So same with multicast. You have a packet, you form that packet from this source machine, and once you send that through, okay, it will be sent to everyone, all these machines that are part of the multicast group. Okay, so they belong to a single multicast group. They have a multicast address, right? The good thing about this is it's used for a lot of things such as video streaming and voice, because the packets, you don't have to send the packets, saves you bandwidth. You don't have to create all the packets just to send separately to all the members of the multicast group. Now, anycast is very similar to multicast. Anycast, however, okay, although the destination address also pertains to a group, this time around we call it as an anycast group. Now, all these 3 are members of the anycast group. They have an anycast address, which is common to all of them. However, when this source sends the packet to everyone, it will be received only by the closest. So only one among all of these will receive the packet, only one, the one that is nearest. And when we say nearest, it means the one that is closest depending on the metrics used by the routing protocols. Alright, so those are the 3 addressing models, and as I've said, there is no broadcast because in IPv6, okay, broadcast is not a feature. Alright, so next one, we'll look at the different protocol headers, header fields basically. And by doing this, we will see some differences between IPv4 and IPv6. So the best way to look at the difference between v4 and v6 is probably, okay, by peeking through the headers. The header is processed by the routers in order for the packets to be transferred between routers, okay, until it reaches its intended destination. It contains some control information. The address is also there, and these things, these control information are used to manage the processing and the proper routing of the datagram as it moves from one router to another. So if you can see here, we have some color coding scheme that we've done. So the ones that are in red, some of them are in yellow, blue, and dark blue there. So the corresponding ones from v4 to v6 have the same colors. So let's start off by looking at the yellow colored header fields. Yellow means fields that have been kept from IPv4 to IPv6. So essentially the functions and everything are the same from v4 to v6. And version is included there. Version in IPv4 has 4 bits, of course, that contains 0100 for 4, and then for IPv6 it contains the binary value of 6. For source and destination addresses, it's also the same. The only difference perhaps is that in IPv4 you only use 32 bits. Okay, so the field size would only contain 32 bits for both source and destination addresses, whereas in IPv6 it will be 128 bits each for the source and destination addresses. Alright, so but the functions, everything, what you put in there, the contents are all the same. Next, the fields that are in red are the ones that have not been kept in IPv6. So you won't see that in the IPv6 headers because these are the ones that we removed from IPv4. Okay, it's not essentially removed from everything, but most of them have been moved as a necessary field into an optional field. Okay, and we will see that later on. That's what we call as a next header or extension header fields. Okay, so IHL or header lengths, identification, flags, fragmentation, offset, checksums, some option values here, and paddings are all removed from IPv6. Why did they remove this? Well, it's because even if in every packet that you send out, some of them contains values for these fields. So not all types of packet requires these fields. If it's not used, it is set to a default value. Maybe it's all zeros, maybe it's all ones, but it is set to a default value. And the router doesn't necessarily have to parse them. Okay, so it just adds up to the workload that is done by your routers. And routers, as you know, has to process millions of packets every minute. So in order to save that, save some time, and save some, make the process faster, they removed some of these fields. So again, the ones in red as an optional field instead. Next, the ones that are in blue or light blue, if depending on how you see it on your screens, are the ones that have minor changes from v4 to v6. Okay, maybe the naming has changed, the values has somehow changed, but essentially it's still very similar to what it was in IPv4. So type of service is now traffic class in IPv6. Total length is now payload length in IPv6. So type of service and traffic class are both used for QoS. Okay, basically classifying the types of packets that are passed through, okay, in order to have some value for QoS. Now total length in IPv4 has been moved as a payload length in IPv6 because, as we mentioned earlier, IPv6 has fixed header length. So we don't exactly need to compute for the header size because you know that it is 40 bytes. So you only have to compute, your router only has to compute for the length of the payload itself. We also have time to live in IPv4, which is now hop limits in IPv6. Now time to live is a timing parameter. Okay, it is in seconds, milliseconds, nanoseconds. And although we'll try our very best to make it same for all the routers, for all the machines that your packet goes through, you can be sure that there is a minor differences between them, minute differences. So in order to avoid that issue, we are using hop limits, which is essentially the number of counts, the number of hops that the packet has to go through before it expires, before it is dropped by the router itself, if it doesn't reach its destination. If you don't have a hop limit, if you don't have TTL, your packet will just move around the network endlessly. So we have to have like a time limit, or in this case in IPv6, a limit in the number of hops before it will be dropped. All right, so we also have protocol there, but it's now next header in IPv6. Okay, next header means that it shows you or it points you to the value or what type of packet follows this IPv6 header. Why? Because we have extension headers in IPv6. So sometimes it points directly to the next one, which is your payload, which is essentially either a TCP or a UDP packet or a header packet, or it can be another IPv6 header. Okay, depending on the value that you see in this field, it will tell the router what exactly follows this header. All right, now we have another one here, which is a new field in IPv6, and that is flow label. Okay, again, this is used for things like QoS and prioritization. It's very similar to traffic class. However, you have more control. There is more granularity with flow label. You can customize, you can create flows, maybe for different types of packet, maybe for voice, for data, for streaming. Okay, you classify them into different flows, and then you can set priorities, whether which ones will be priority on the network first and such things. You can do that with flow label. Alright, so those are the different protocol headers in IPv4 and IPv6. So just to recap what we found there, we said that IPv4 uses 20 octets or 20 bytes, but it has 10 basic header fields compared to 6 only in IPv6, right? Also, IPv6 has 40 bytes in the header. However, it is fixed size. Although it's twice the size of IPv4, it's fixed size. IPv4 is 20 to start with, but it can grow more, it can grow bigger depending on the values that you add on some of the fields here. So although this is bigger in size, we essentially have a smaller number of header fields, less parsing by the routers, easier and faster processing by the routers itself. So essentially, the performance-wise, it should be faster than IP version 4. Any questions? Now let's look at IPv6 addresses. Now, as I've said at the beginning, we will not go into too much detail about IPv6 addresses. However, this being an overview, I want you to be able to identify IPv6 addresses if you see them. So we'll just look at the format of IPv6 addresses here. We know that IPv6 addresses are 128 bits, so it's not 32 bits anymore. We are not going to use the text representation that we do with IPv4, which is what? It is using dotted decimal format. 10.20.100.1 is an example of IPv4. 192.168.100.10 is an example of IPv4. The way we write them down is from 32 bits, we group them into octets, 8 bits, and each octet is separated by a dot. And then each of these octets are then converted into decimal. That's why we call it a dotted decimal format. In IPv6, however, we are not going to use decimals, we are not going to use dots. Instead, we are going to use hexadecimals. So you have more range of values in a hexadecimal value. That applies to each of the 4 bits in an IPv6 address, which is also called as a nibble. Alright, so a nibble is equivalent to 4 bits. And each of that can be converted into a hexadecimal value from 0000 all the way to 1111. So that's from 0 up to F if it's hexadecimal. Okay, so you will see some letters as values instead of just using numbers as we're used to in IPv4. So as we said, IPv6 is 128 bits. So if you write them down as hexadecimal digits, that is about 32 hexadecimal digits in an IPv6 address. Okay, and from there we subdivided into what we call as groups or fields, and each of these fields are separated by a colon. So we're not going to use dots, okay, because it is already used by some other formats in uses the MAC addresses. So we're not going to use that. Instead, we are going to use colons. So each of the fields here, each of the X values here is equivalent to 16 bits or 4 hexadecimal digits. All right. So as an example, this is a complete IPv6 address. As you can see, there should be 1, 2, 3, 4, 5, 6, 7, 8. There should be 8 fields, and each of the fields are separated by a colon here, okay? And each of the field consists of 4 hexadecimal digits, okay? It's quite easy, however, it is long. So it's very hard for us to remember IPv6 addresses compared to IPv4, right? You can try, but yes, it's very difficult to remember, especially if you're using a very long or a complete IPv6 address. Now, the moment that you have your IPv6 blocks, perhaps from a registry, from IPNIC, or from your upstream providers, most likely when you start using them, you will be using the first block. Maybe out of a /32, you will be using the first /64. So you will notice later on that there will be lots of zeros. So there are ways in which you can try and remove the zeros from your address, and that's what we call as an abbreviation, okay, a shortening of your IPv6 address. And how do we do that? One, if you have any leading zeros, you can remove it. So in this case, in this second field here, you have 0 dBA. You can remove the 0 and just write them down as dBA. Okay, that's pretty straightforward. If you have a 036E here in this sixth field, you can just write it down as 36E. However, 1250 and 2B00 here should not and cannot be abbreviated. You cannot remove the zeros because it is in the it's trailing. It's not a leading zero, right? What else? If you have groups of zeros, different fields that are adjacent to each other, that are all zeros, can be abbreviated, can be removed altogether, and then represented as a double colon. Okay, so see here, this here is a double colon, and it represents 3 fields. Now, you can only use a double colon or a null value once in an IPv6 address because otherwise it will be vague. Okay, so only once, because you know that there should be 8 fields. If you are using a double colon there, you can discount the number of fields that are present, and you know that the rest are represented by a double colon. So in this case, 3 fields are represented by our double colon. So I think if you're looking for a symbol that represents IPv6, it's essentially this, the double colon, right? Next, IPv6 addressing structure. Now, I briefly mentioned about the hierarchy or the distribution of IPv6 addresses earlier on, which is from IANA, it's distributed to the RIRs. From the RIRs, it's distributed to the local internet registries or your ISPs or your upstream providers. And from there, it is distributed to you or to customers, maybe home users, maybe enterprise users, maybe governments, academic institutions, all of that, okay, obtain their IP addresses from that hierarchy. Now, from looking at this diagram, you can have a sense of that linkage as well. Now, as you know, 128 bits is the number of the size that we use for an IPv6 address. That's why we have here from 0 all the way to bit 128. This is the size of the address that we give, that we assign to a device. So each device has each device's IPv6 address has 128 bits. That's why we have here device. Okay. Now, somewhere in the middle here, we have at the bit number 64 and 65, we have like say a division. We divided our IPv6 address into two: a network address and an interface ID. Okay, so your network prefix, you can think of it as similar to IPv4 structure. In IPv4, we have the network bits and the host bits, right? Host bits is assigned, of course, to each of the hosts or devices that are within a subnet, and network bits, network prefix, is what we assign on a particular subnet. Okay, so similarly, we have this structure in IPv6. We have a network prefix and we have an interface ID. The interface ID part is at bit number 64. Now, this is not negotiable. Okay, with IPv4, we change the values of the network bits and the host bits. You can make the host bits as small as possible, even up to /31, which means you only have one bit extra or 2 bits extra for the host bits compared to your network prefix. With IPv6, interface ID is always 64 bits. At least now, nowadays, that is what we're following. Okay, maybe it will change in the future, but as of this time, when we talk about interface ID, it is always 64 bits. Now, this 64 bits will be assigned to the machine, to the host. Okay, you can assign that in different ways, which we might be able to look at in the following slides, but essentially, it can be based on the machine's MAC address. It can be manually assigned. It can be taken from maybe a DHCP server or other things. Okay, it can be randomly assigned by the operating system as well. But essentially, your interface ID is a 64-bit value. Okay, that is always stays that size. Right now, let's focus on the network prefix for the time being. So 64 obviously would be the smallest size of a subnet that you can assign. Okay, that is because, again, from here all the way here is your interface ID and it's not negotiable. So the smallest network prefix, the smallest size of IPv6 space that you can assign to a single subnet, to single network, is a /64. So whether you have 2 computers, 2 machines, or maybe 100, or maybe 1,000 machines connected to a single VLAN in your network, then you will assign a /64 to that. If you have a point-to-point link, okay, what we're recommending at this point is to assign the entire /64 block to that point-to-point link. So obviously, you only need 2 addresses for a point-to-point link from one of your 2 end nodes, but we are going to assign the entire /64 for that. Is that clear? Now, let's go back a little on here. We have ISP/32. This is the size that ISPs, service providers, upstream providers, would get from a regional internet registry. So if you come to APNIC, if you're working for an ISP, come to APNIC, request for your IPv6 address, you will be provided, you will be given a normal maximum of a /32. This doesn't mean that you cannot request for more. So if there is a need to request for something that's bigger than a /32, then you can always do so. However, okay, normally we give a /32 that is based on the current policies. Now, if you think about it, /32 is already very big. /32 is equivalent to the size of the IPv4 address space, right? So IPv4 is the entire /32 already. From this /32, upstream providers will now distribute that to their customers. These customers can be smaller ISPs It can be enterprise users, big corporations, or small home users. So it varies. So you have the option to provide anything that is smaller than a /32 to your customers. Normally, it ranges from a /64 to a /48. /64, you assign that again when your customer is only using one subnet. Maybe it's a home network and you're not expecting that home network to grow, then you can assign a /64. If, however, you have a medium-sized company as your customer, maybe /48 is too big for them, so you can assign something that's smaller. Normally, that is somewhere between 48 and 64, which is a /56. Okay? If you notice, when we do the assignments, we use values of factors of 4. So it's within the nibble boundaries. It just makes it easier to do that. So it's up to you, but it is recommended to do the assignments using the nibble boundaries because it avoids any human errors. Right? Anyway, as I've said, you can assign something that's between 48 and 64 if you have a medium-sized company. And if you have, let's say, a big multinational corporation or organization as your customer, then maybe you will assign a /48. So that means that if all of your customers are assigned a /48, you can have a single ISP with a /32 block can have 2⁻16 possible customers, okay, which is this size difference here. All right, so is this clear to everyone? All right, I've briefly mentioned about interface ID earlier. So interface ID is your lower order 64 bits of your IPv6 address. It can be assigned in many ways, okay, the most common of which are using this modified EUI64 and also using this auto-generated pseudo-random numbers. As I've previously mentioned, it can be assigned in many other ways too. It can be manually configured. You can assign it via DHCP-v6, or possibly there might be other ways in the future. However, as I've said, the most common is using EUI64 and pseudo-random numbers. Modified EUI64 is based on the MAC address. Your machine has a unique MAC address. It is 48 bits. It's not 64 bits. And since we needed it to be 64 bits, there's a way, okay, you don't really do it yourselves, but your operating system will do it. It will add FFFE somewhere in the middle of your 48-bit MAC address. Okay, and then from there, it's modified again because there will be changes in the 7th bit of the 64-bit address that you currently have, depending on whether it is unique or not. Okay, so essentially, this one is based on your machine's MAC address. And your machine has a unique MAC address, so wherever you go, it doesn't change. So your interface ID will not change as well. So for some people, it might be an issue, especially when it comes to privacy. Therefore, they've come up with using pseudo-random numbers instead. With pseudo-random numbers, your machine will decide values. It will just generate some random values and assign for your interface ID. That's it. Now, most operating systems, newer versions of Windows and also Mac OS X, I think uses pseudo-random numbers. Older versions such as Windows 98, I think even Windows 7, or the earlier versions of 7 uses EUI64. If you're using Linux, I think the default is still using EUI64, but you can always switch to either one of these. Just need to do some commands or execute some commands there. All right, so that is your interface ID. Now this is the global network prefix. So if you get an IPv6 address, it should be within this range. This is equivalent to the global address or the public address as in IPv4. As you know, it's unicast, okay? Unicast address, and the range will be 2000:/3, right? So all publicly available blocks would be coming from this range. Now from this /3 block, each of the RIRs were given a /12 block. So APNIC has got a 2400/12. ARIN has got their own /12, AFRINIC, LACNIC, and also RIPE NCC. Okay, so from here you will see that, are we on time? Yeah, I think we're over time now, but anyway, we're about to end soon. But basically, if you request your block from APNIC, because we're in this region, then you will most likely have a block that's somewhere in 2400. Alright? This is the entire size of the IPv6 address. Now our global unicast address, which is 2000/3, is just this. It's 1/8 of the entire IPv6 space. 1/8. So you can think of it as a piece of a pie or a pizza. Okay, so you have a slice from there. Okay, from that /3, this is now with IANA, and from that /3, we have given 5/12s to all the 5 RIRs. There's one /12 that is also used, but it's for some other things, maybe miscellaneous. Some of the experimental blocks are here, some of the private blocks are here, unicast, anycast, multicast blocks are also here. So that's 1/12. So that means that within IANA, they still have 506, because altogether there should be 512/12s in a /3. So right now, IANA has 506 of them, because all the other 6 has been given away. So the moment that we've run out of IPv6 in our region, maybe we've all used up this 2400/12, we can always go back to IANA, and there's 506 more left. Right? So that just shows us how big the address space is. Okay? So if you don't have an IPv6 address yet, please come and claim them from APNIC. There is a program called Kickstart IPv6. If you're not a member yet, you can apply for both IPv6 or IPv4 request and also membership. And if you're already an APNIC member, you can get your IPv6 addresses by simply logging into my APNIC and claiming your IPv6 address blocks. That's it. It's very simple, and IPv6 is gaining a lot of changes, traction these days. So you'll see you will see the rapid growth of IPv6 compared to how it was in around 2008 and 2009. 5 years later, we are somewhere around 16,000 prefixes. This is still a lot less than IPv4, but you'll see the growth, okay, is very good, and it's very promising. All right, so I think that must be the end of it. So yes, that's the end of our session. If you have any questions, please write them down in the chat. Otherwise, I'm gonna write down the link to our survey, which is this. So any questions from the class? All right, I don't see anyone typing anything. So this is the link to the survey. If you can fill it in for me, I'd be very glad if you do that. If you want a copy of the slides, yes, I was just about to say that, Noel. It is available on our FTP. Once you have completed the survey, you should be automatically redirected to the link to the FTP. As I don't have the link with me right now, otherwise I could have written it down in the chat. But yes, please fill out the survey. After that, you will be automatically redirected to the FTP site, where you can download a PDF copy of all the slide handouts, materials that we are giving out for today. All right, so that's it. Any other questions or inquiries? If not, I think we will end there. Thank you very much, everybody, for your time and for your attention. It's a very limited amount of time to cover everything about IPv6. We have another session later on, I think, which is about IPv6 addressing and subnetting. So if you can join us, please do join us at 4:30 in the afternoon, which is about roughly 50 minutes away. Yeah, 50 minutes from now. So please do join us there. Otherwise, if you have other questions later on that you can think of, please feel free to send me an email at cheryl@apnic.net. All right? So thank you again, everybody. And